Professor,
Yes.
do we have any Zoom session before the midterm that we do
Yes.
sort
Yeah.
of
We're doing
example?
yeah, so problem solving session. We can have it in person or Zoom, up to you. What do you prefer? Zoom?
Because I don't have time to do it in person, you know.
Yeah. Okay.
I mean, you can record a session in person, can't
Yeah, yeah, yeah. So
Some
from
people
it's better
enjoy
to have it in Zoom because in Zoom is better.
Yeah.
It's easier to record here. I'm not sure how we're gonna record it. Anyway. Okay, any questions before we start? Okay, so today gonna continue the feedback topic. I believe. So we're talking about the feedback, block diagram, the negative feedback, advantages of feedback, disadvantages of feedback, and we talked about each advantage individually, and then we mentioned the four possible topologies for feedback. We can have voltage amplifier, current amplifier, transconductors amplifier, transresistance amplifier. And each one has a different name in the feedback. So the voltage amplifier, you sample the voltage in shunt and you mix it in series. And be careful because some references in textbooks they use the other, reverse name. Okay, so you might find a reference that calls this one shunt series instead of series shunt, because they believe that it's an output over input. Like it's the relation between the output to the input, not the input to the output. So, but the convention that's used in this reference is input first, how input is mixed, and then which is series, right? This is series with this one, right? And then how output is sampled or is measured. So it's shunt or parallel. You might find also another alternative way which uses what is the quantity that's sampled and how it's mixed. Okay? So you might find like what's the quantity that's sampled here? Is it voltage or current? When you sample in parallel.
It's like voltage.
Voltage. So this is known as voltage. Oops. Voltage series. So this is another way of calling them. You might find a reference that will call this circuit voltage series. Okay, but we're gonna follow this. Okay, and this one, for example, this is you are sampling or measuring the current. This wire connected in series, and you're mixing it as a current, so you're mixing it in shunt or in parallel. But according to this is going to be current shunt. Okay. Sometimes they call it this way because you are measuring or sampling the current at the output, and you are mixing it as shunt, as a current. Okay. But as I said, we're not going to follow these conventions. We're going to follow the textbook convention, which these ones, okay, are these ones. And another one, this is, as I said, this is voltage controlled voltage source. This is a current controlled current source. This is voltage controlled current source, and this is a current controlled voltage source. Okay. And we start seeing how to analyze the basic feedback configurations. This is called direct analysis. Okay, so we do direct analysis under certain conditions. you can see here the beta or the feedback function does not load the actual amplifier, right? So this is very high impedance, so there's no load here. So if this is the case, it's easier to use the direct method like this, okay? However, if you have an impedance here, because this one is indirect, is not an ideal circuit, so most likely you're gonna have another resistance here, okay, and another resistance here, right? Because this is also an action amplifier, similar to this one. So this one has an input differential impedance, this one also has an input differential impedance. This one has an output resistance, this also has an output resistance. But this one goes this way, this one goes this way, okay? So if this is the case, analyzing it directly like this is very complicated, okay? And we try to avoid that by methods that I'm gonna show you how to do that, okay? So for the series shunt or the voltage amplifier, I think we proved these ones. Okay. I think we proved this one, right? Yes.
If I may ask, on the previous slide and this slide, what type of devices might you see these things in?
As I said, this one could be transistor amplifier or operation amplifier, and this one most likely is a resistive network.
Okay,
Voltage divider, 2 resistors, 1 resistor, something like that.
so you have an amplifier that's
Yeah.
feeding the,
Yeah.
a device on the.
Something like this, okay? So where's the A? This is the A, and it's made out of operation amplifier. Where's beta? Beta is, or B, is a resistive network,
Okay,
okay? Let's do this one. Where's the amplifier? Where's A? This is A, the amplifier, and this is the
well,
feedback network, okay? Here, same thing. Where's the amplifier? These two together, and you go like this way, and this one brings the output back to the input. Okay, so this is the feedback network.
but okay, so but you've got the amplifiers, is that in blue, is that a device that's being amplified? Or?
No, the blue one is just a resistive voltage divider, right? It's just 2 resistors.
Okay,
Okay, but we highlight them here to indicate that this is the feedback network. Okay.
but what would you use these, what application would you use, just,
Okay, when you build an amplifier, okay, without feedback, I can remove this feedback, right? I can remove this feedback, right? So I can have this circuit like this. And you tell me how to modify this without feedback, okay? So this is the first transistor. Okay. Okay, and this is the RD1, and this is the second transistor. And this is RD2. And this is grounded, and this is the output, right?
yes,
Now I removed that feedback, right? There's nothing going from the output back to the input, right?
right,
But can I leave this amplifier like this? Like if you remove, remember this was connected to the feedback, right?
yes,
Do you think this amplifier circuit is gonna work?
no,
No, because if you remove this, you have to see how it was connected at the output and how it's connected at the input, right? Now, this feedback network, how is it connected to the output? Is it parallel, shunt, or series?
that looks
It's-
like series,
No.
no, it's not.
So you are measuring voltage, right?
Oh, okay,
So you
voltage.
take the
goes across,
voltage
right.
and
Yeah.
make like voltage divider and then mix it down.
Okay, so
Okay.
you're measuring voltage across.
One way to recognize this, by the way, if you find the feedback network and the output are in one node, most likely this is a parallel or a shunt connection, meaning that you are measuring voltage. Okay. On the other side, this voltage, now I took this voltage V out and I attenuated because this is an attenuation. This is not amplified. There's no transistor here, right? This is a resistive network. So this is an attenuation, right? If you have a resistive network, it will do attenuation, right? So this voltage most likely is less than this one, right? So you took this one and you come up with the feedback, V feedback. Now you mix V feedback with Vs. How did you mix it? Are they in series or in parallel? Did I mix this voltage in the input circuit? So I sample from the output circuit and I mix into the input circuit. It's a series. Why? Because the one way to recognize this, if the two terminals of the feedback output, both of them are in the loop of the input circuit, that means a series connection, right? This R1, you can see R1 terminal and this R1, the other terminal, both of them are in the input circuit, right? So that means the feedback voltage is mixed in series.
And the ground connection is what?
Yeah, the ground connection here, yeah? This is a short, right?
Does that tie them back together to continue it going back to the
Of course,
input?
yeah, this is connected, yeah. But in electronic schematic to simplify, this is connected, all these points are connected. Okay?
Oh, yeah, I understand that. I'm just trying to think to myself, okay, so you have like 3 volts going through R2, through R1. Does that 3 volts or whatever is comes to after it goes through the
Yes.
resistive network? Does that voltage go back into the?
Yes. Like if you have a 3 volt here, right?
Yes.
And let's say this 3 volt after the voltage divider becomes 1 volt.
Yes.
Okay? This 1 volt and this one, they are in series, right?
Yes. Okay.
Like in what way? Like can you give me the relationship between Vs, Vi, and Vf? With these polarities. Vs, positive, negative. Okay? Vi, positive, negative.
Yes.
Vf, positive, negative. So can you write the KVL?
Starting at that node
Yeah.
between VI and VF at that node.
You'd like to start here? That's fine. And you're gonna go this way or this way?
I'm gonna go the first way going down.
Okay, so plus Vf.
Over
Right.
R1.
No.
Oh,
Voltage,
VF plus
just voltage,
Yeah, right,
just
right, right.
voltage. KVL, just add voltage.
Voltage.
No, not
I
add
times
times.
R would be the
So
voltage.
you finish here and then you're gonna go this and this is negative,
VS,
right?
negative
So
VS.
minus Vs. Okay, then
Plus
plus
VI.
Vi equals zero, okay?
Okay.
Can we rearrange this to bring Vi on one side and everything else on the other side?
Oh, yeah, sure.
So Vi equals,
Negative, VS minus VF.
okay? So this is exactly this one. Vi equals Vs minus V.
Okay,
So I measured the V out.
yes.
I applied V out into a network. Most likely this is a resistive attenuation network. Could be, by the way, frequency selective, but this is something else. Then the output of this, which is Vf, is subtracted from a voltage, Vs,
Yes.
to give you the input to the amplifier,
Fire, yes.
right?
Sure.
So Vi, what's Vi in this circuit?
VI is the input to the transistor.
Exactly, what's it? VGS,
VGS.
right? VGS is the voltage that gives you the output.
Yes.
Remember the output, if you draw the equivalent circuit, the output depends on VGS, which is Vi. Okay. So now, let's go back to the first question. Why we do this? Why we have to introduce that feedback, right? Without feedback, if I decided to remove this, now remember this was connected in parallel or shunt, so it doesn't matter. So if I cut it here, this is not going to affect the circuit, right? Circuit's still the same, right? However, this one is connected in Series. If I remove it, now this emitter is going to be floating, right?
Open circuit.
So what should I do with this? I put it to ground. You know, I have to short it, right? To remove completely the effective feedback. So this was the original circuit. So the first designer has this, and this is VDD, and these are Q1 or M1 and M2, okay? Okay, and this is VS. Now if I ask you, what is the gain of this circuit?
Well, if you don't have an R2 and an R1, is there a gain?
Yes, there is. You have to find the gain of this stage, then the gain of this stage, and they multiply them and give you the overall.
Could it be GM RD1 for M1 and then for M2 GM RD2?
That's correct. So the gain here is GM1 RD1, GM2 RD2. Okay. Why is that? Okay, let's if we'd like to do it in a more detail as we did this in a KVL, okay. But as I said, in this course, I need you to, you know, like work faster in solving problems. You know, if you are not sure, you can just replace this transistor with its model. Replace this transistor with its model. Short the DC. Okay, so this is going to be like this. And this is what's this?
GM.
This is 1 over GM. And this current is GM VGS. And where is VGS? This is VGS, which is VI. Okay. And then what's going to happen to this resistance? This one becomes ground, this one becomes ground. Right? And this one also, same thing. 1 over GM2, this is 1. Okay. And this is VGS2, GM2. Okay. And where is VGS2? This is VGS2. Okay. Now, since this one is connected from this point to the ground, I have to bring it here, right? So I can just expand this. Let me just erase this because I'd like to add this resistance here. So I'm gonna draw this one again. So this one comes here. This is RD1. Okay. And then right? And then you have RD2. And this is V dot. Now I can analyze this, start analyzing this circuit, right? Okay, now this is VGS2, right? Right. So this point here, this node is VGS2, right? From this point to the ground is VGS2. Now what's the gain? The gain is V out over VGS2 times VGS2 over VGS, right? V out over VGS2 times VGS2 divided by VS. Let's take them one by one. What's V out? What's V out over VGS2? This current is GM VGS2, right? So So this current is same, right? So V out is this current times this resistance, but with a negative sign, right? Because this current is gonna go this way, making this positive and this negative. However, V out is measured this way, right? So there's a negative sign, right? The negative GM2 VGS2 times RD2 divided by VGS2. This cancels and this becomes negative GM2 RD2, which is this part. Okay. So this is this one. Sorry, this one. This one is this one. That one. Now, how about VGS? Two times divided by Vs. How much is this voltage? Yeah, this current is GM1 times VGS1, right? And this current is the same, right? Now, to find this voltage, you have to take this and this in parallel, right? But are they in parallel in reality? No. Why? Because this is open, right? This is the gate. Remember, this was like this, right? So this is the gate of a MOSFET transistor. And the gate is isolated, right? So the current here is 0, right? There's no current. So in reality, this and this are not in parallel. Why? Because you have an open circuit here. So you need just to multiply this by this. So VGS2 is nothing but GM with a negative sign, GM1 VGS 1, sorry, VGS1 times RD1 divided by VS. What's VS?
VGS1.
It's VGS1, right? So this is VGS1. They cancel this, and this gives you negative GM1 R1, which is this part. Do you have two negatives? Okay, they're gonna cancel, because this was negative, and they're gonna cancel, and you end up with no negatives. Okay. So again, if you're not confident, try to use the equivalent circuit and solve it this way. It's going to take longer time, but you feel confident. And again, I use here what model? T model or hybrid pi model? T model, right? And it makes it more difficult, right? If I use hybrid pi model, it's going to be much easier than this. Okay. I told you, if you have a transistor that has the drain, the source grounded, use the hybrid pi model. So T model makes it, looks, you have to think of this, and so on. Okay. So let's go back. If you remove this, your gain is GM1 RD1 times GM2 RD2. So it's a kind of GM squared times RD squared if GM are the same and RD are the same. However, if you do the feedback, this is your gain. It's not GM1 RD1, GM2 RD2. No, it's this quantity divided by this quantity. This quantity is positive, right? We agreed that it's positive because there's no negative here, right? Negative times negative is positive. So this is a positive quantity, and this positive quantity is large, right? So let's assume this was 1,000 or whatever. Now you divide this quantity by 1 plus another quantity, and this is the same as this one times R1 over R1 plus R2. If this is very large, then this part is the same, multiplied by a fraction that's not very small. Somehow it's not that small. So you still have this number here is very large compared to 1. Right? So you can remove this one compared to this thing, and then cancel this with this, so this is going to give you R1, 1 over R1 divided by R1 plus R2. So you reduce this gain, instead of having this large gain, this is a very large gain. So after feedback, so this is before or without feedback, the gain is this, AV is this. With feedback, the gain, I'm going to give it a subscript F, is roughly R1 plus R2 over R, which is 1 over B or beta, which is 1 plus R2 over 1. So this is smaller than A, this one. So this one here is much smaller than this one. Okay? So by the feedback, the gain is reduced. And this is one of the disadvantages. Okay? So with the feedback, you reduce the gain. However, with that feedback, you get all these advantages. Now the gain, is it function of GM anymore? No. And GM is a transistor parameter that could change because it depends on that process and the transistor itself. It reduces nonlinearity, it reduces the effective noise, you can control the input impedance is going to be higher and the output impedance is going to be smaller in this case, and the bandwidth is going to be large. So you do the feedback in this circuit, and instead of designing this circuit without feedback, you put this feedback, you pay some price of reducing the gain, but you get other advantages of increasing the input impedance, reducing the output impedance, having the gain less sensitive on parameters, the transistor parameters, and increasing the bandwidth, and so on. So this is the main idea. Okay. So the circuit without feedback has much larger gain, which is good, but it's very sensitive to other variations and very, affected by other things. And the bandwidth is not large. It has many disadvantages. So instead of saying like, okay, I'm gonna get one large gain from one stage, I can solve this by scaling several stages and get the larger gain from these stages. But each stage has to have a feedback to be more robust and stable, and higher bandwidth, lower improved input and output impedance, lower noise effect, and so on. So instead of designing just open loop gains with no feedback, I design circuits with feedback to improve the circuit performance, or the amplifier performance. So this is the main idea. Okay? Let's take this example again. Okay, so this is another example. So this one has one transistor, so it would be easier in analysis. So let's analyze this one and see before and without feedback and with feedback. Okay. So if you'd like to design this without feedback, what are you going to do? First of all, what configuration is this? Is it common source, common gate, or common gate? Because the input is applied to the source, the output is taken from the drain, so the gate is common. If you design this without feedback, it's going to look like this. Completely without feedback. Okay? you have to disconnect the feedback network from the output and from the input, right? Now this feedback is connected to the output in parallel, shunt, right? Because the node of the network and the node of the output, they are common. So this is parallel or shunt. However, it's added to the input in series. So if you cut here, you don't need to do anything. You don't need to short circuit this, of course. You're not going to short the output, right? So you just remove it. You cut here and remove it. If you cut here, this is going to be floating. So you have to short it. You have to remove the effect of feedback. Instead of adding or subtracting VF from VS, you just subtract nothing. So you short circuit VF. So this has to be shorted. And then you have RD1, or RD in this case, and this is VDD, and this is the out. That's it. So this is the same circuit without feedback, and this is ground. Right? Now, how to analyze this? Well, it might not look easy to analyze it without drawing the equivalent circuit, so let's draw the equivalent circuit. This is common gate, right? So what configuration works best? T model, okay? So I'm gonna connect T model, so we're gonna have this, okay? And then you have G1 over Gn here, so it's gonna be like this. And then current source, and then this is gate, and it's shorted to the ground, and this one RD, and this is V. Okay? So this is the gate, this is the source, and this is the drain, right? So this is the source, this is the drain, and this is the gate. Okay? You can see that the source is connected to VS, which is here. Okay? And this is the model, and gate is connected to the ground. Drain is connected to RD to the ground because this is going to be grounded. You know, the AC analysis, VDD is 0. So this is the AC ground. Then this current here is GM VGS, right? So this is GM VGS. Where is VGS? This is VGS, right? Actually, it's the other way around, right? This is positive and this is negative, right? Because it's from the gate to the source, not from the source to the gate. So this is VGS, right? So this is VGS. Can we analyze this one and find the gate? So the gain with no feedback, without feedback, is V out over Vs, right? What's V out? Okay, this is the same current, and this is V out, so it's going to be GM VGS times RD, the negative sign, divided by Vs. What's the relationship between Vs and VGS? They are equal but opposite, right? So this is Vs with this positive and this negative. So the positive is here and the negative at the ground. This one, the negative is here and the positive is the ground. So this is the same as negative VGS. You cancel this with this, you cancel this with this. So this is GM RD. It's exactly the same as the common source except with the negative sign. I told you many times that the only one that has a negative that inverts the input signal is the common source and common emitter. Common drain, common gate, common base, common collector, they do not inverse or change the polarity of the input. So if you design this circuit without the feedback, this is your gain, which is nice and large. You can control it with RD, right? Increase RD, increasing the gain, that's fine. However, we decided to do this circuit to make this amplifier more robust. Increase the bandwidth, improve the input and output impedance, reduce the nonlinearity, increase the immunity to noise, and so on. So to have all these advantages, we decided to remove this terminal from the ground, take a sample of the output, not the whole output. So I'm going to do a voltage divider, and then connect this back. So now the gain is going to reduce. And the question is how to find the gain in this case. Well, if you do the direct analysis, it's easier to assume some. So how can we introduce this circuit here? It's going to be here, right? So this one here, V out. We're going to have R2, R1, and then we do this. Okay. Now the analysis is going to be complicated, right? But it's not easy to analyze this circuit. So it's always good to assume some or have some assumptions. Okay, and of course, if you add RO, we didn't add RO in the first case, but if you add little RO, which is connected here, this is going to make it more complicated, right? So if we assume RO is infinity, and we assume also R1 and R2 do not load, both of them, or series connection of R1 and R2 does not load RD. They are not, like if you now you can see that R1 and R2 in series are in parallel with this one, right? These two are in parallel with this one. Okay? So let's assume that this parallel combination is not, R1 and R2 are much larger than this one. So there's no loading effect from beta on the amplifier. Okay? So how can we analyze this? How can we find the gain? I'm going to find the gain only. Okay? Well, let's start with this. I think we have it in another slide. Okay. So let's do it this way. Okay. So let's find the gain in this case. Okay. Now the gain AV feedback Again, it's V out over Vs, right? Okay, what's V out in this case?
Should be the same expression as before. Because of R2 and R1 being so much greater than R2.
Yep. So, if let's assume that we are not assuming R1 and R2 are very large. Let's assume that they are, close to RD. What do you think?
R1 plus R2.
So this current now is not passing through RD only, right? It's passing through R1 and R2 in series, and the series combination is in parallel with RD, right? So this one is going to be minus GM VGS times RD in parallel with R1 plus R2. Right? Okay. What's VS? Now, before this was ground, right? When this was ground, VS and VGS were the same, but now they are not. Okay. So what's VGS? So I'm going to write it here. VGS is VG minus VS, right? Any volt between 2 points or 2 nodes is the volt of the first node minus the volt of the second node. What's VG? VG is this one, right? And VS is this one, right? So what's VG? No.
It's the
VG is the same as this voltage here.
So VO is across both.
And what's the voltage here? VF. This is the feedback voltage, right? I'm taking a sample of V out by dividing V out among R1 and R2 and taking this feedback. So this V voltage is called VF. So this is going to be VF, which is a voltage divider of V out among R1 and R2, minus VS, VS, which is VS. Here VS is the subscript of S and VS is the source, okay? So it's the same thing, okay? So it happens that they are the same, right? So minus VS, right? Why we're doing this?
we still need to figure out.
Because we need to find a relationship between VS and VGS, okay? So this is, we cannot remove this and put VS, right? VGS and, we cannot remove VS and put VGS. So now what's the relationship between VS and VGS? So VS, this one, okay, is VGS from here. VS, if you remove this to this side and remove this to this side, right? Okay, so let me before this, okay, let me define VS. So VS is what? VS is VGS minus VG.
Should be
The other way around.
The other way around? Oh yeah, sorry. It's VG minus VS. VGS. Is that correct?
Yes.
Yes. Yes, that's right.
Okay. Okay. Which is VG, we said it's VF, minus VGS. Right? And what's VF?
Volts division.
It's V, exactly. VF, it's V out times R1 divided by R1 plus R2. So in this case, this is going to be V out R1 divided by R1 plus R2 minus VGS.
Yeah, that's gonna be the same.
If you did the parallel thing, something that would cancel.
I'm missing something here, I don't know what. So at the end, this is going to be, we should look like that. AV feedback, it should look to the GNRD divided by 1 plus GN, and RD is multiplied by whatever RD times R1 over R1 plus R2. So what am I missing here?
Well, we have V out on the ball. Seems like you've got a recursive relationship there.
Yeah. VS VS is VG minus VGS. That's correct. And VG is V feedback minus VGS. Oh, yeah. Okay, that's correct. Let's just remove this and put this. Agree?
Yes.
So if I remove, this is V out, right? So if I remove this and put this, you're gonna get something like this. I know it's not easy, but let's do this. You agree up to here, right? So I can erase this, right? So I'm gonna replace this with all of these, right? Okay, so this is minus GM VGS RD in parallel with R1 plus R2 divided by minus GM VGS RD in parallel with R1 plus R2 times R1 divided by R1 plus R2 minus VGS. Agreed? Now I can cancel this VGS,
Whole bunch of negatives.
and this negative, this becomes positive, and this also becomes positive, right? And now you have the gain is GM This is 1, right? 1 plus GM RD parallel with R1 plus R2 times R1 over R1 plus R2. How much was the gain before? So this is AV feedback. Okay? AV without feedback at all was just GM RD. Now it becomes GM RD parallel to this divided by this one. If this is very large, we can cancel this one with respect to this one. And if we cancel the one, this becomes, we can cancel this, and this roughly becomes R1 plus R2 divided by R1, or 1 plus R2 over R1.
In practice, you probably just adjust RD to account for the feedback, right?
RD,
Yeah, so RD in parallel with R1 plus R2.
yeah, we need to adjust RD to make sure that R1 and R2 in series, they're much larger than RD. This one.
I was just thinking so that once you take them in parallel, you would end up with the same impedance to ground.
What do you mean? Can you say that again?
So the
RD in
you
parallel
take-
with the series, okay.
Yeah, so you want that to remain constant as you add in the feedback, right?
What do you mean by remain constant? They are constant anyway.
Well, before,
Oh.
when you're talking about just AV, you just have the RD.
Oh, RD, okay.
So you would adjust RD to account for the presence of R1 plus R2, right?
Yes, yes. Okay, so this is definitely less than GMRD1, okay? Much less than GMRD, much less than this one. Okay? However, this circuit with the feedback provides more stable circuit. I mean, less sensitive circuit to the change of parameters in the transistor, because it does not depend on GM, right? This one just depends on the output, the feedback network, right? The R1 and R2. It provides larger bandwidth, it provides larger input impedance, smaller output impedance, and so on, okay? But as you can see, if you analyze the circuit directly, it's not easy. Okay, so let's see how we analyze the circuit in a more systematic approach. Okay, so let's go back here. So this is the shunt series circuit. Again, here we assume for the direct analysis, we assume always that this circuit does not load this one. So similar to the fact that R1 plus R2 is much larger than this resistance, okay? In this case, since this is ideal and this is current, this has to be shorted, right? Because this is a current amplifier. So a current amplifier has to interact, because if you'd like I/O to be exactly the same as this current, this has to be much larger than this one, or this one should be short circuit. So if now I/O is the same as this current, right? Because if you have a current that flows this way, all this current is going to become here, flows here, because RO is much larger than a short circuit. If you short circuit, the current is going to pass through the short circuit. Okay? So let's do the analysis and find the gain before feedback and after feedback. Before feedback, if you remove the feedback, what you're going to do, if you remove this, what you're going to do to this side and this side. If you remove the effective feedback, would you leave this open? So you have to short this one. Why? Because it's connected in series. So you have to short circuit here. And if you take this off, you don't have to do anything because it's connected in shunt or parallel. So without feedback, the gain is AI, right? With the feedback, let's analyze the circuit. I/O is the same as AI times II. You agree with that? Or is this clear why this current is the same as this current? Because this is shorted, right? If this is shorted, that means this is shorted, right? Now, if you have a current here, this is going to be the same as this current, because no current will flow through RO, right? If you have a resistance in parallel with a short circuit, what's going to happen to the current? You think the current will leave the short circuit and pass through RO? No, all the current will go to the short circuit, because it's a highway, right? Okay, so IO is the same as AI, and with the same direction, right? So there's no negative sign here. Now, what's II, the input current? Well, the input current is this one, which comes from the subtraction of this current minus the current that's taken to the feedback network, or comes from the feedback network. So II is IS minus IF. And here we assume just RS is very large, just for the sake of simplicity, okay? So RS is very large, so this current will go this way, nothing is going to go here. If this is infinity, so you can remove it. So IS is here. Part of it is going to go at IF, and the output or the input to the amplifier is the current I sub I. Again, this is the same equation as the feedback block diagram. So II is IS minus IF. Then, what's IF? What's this current? Well, this current is a fraction of this current. This is the feedback current. So the feedback current I sub F is beta, which is the gain of this, or actually this is an attenuation of this feedback network, beta I times IO. So substitute IF with beta I times IO. Then you multiply AI on both sides, you get this. Then you have an equation that links I out and IS. All what you need is to rearrange, making I out in one side and IS in the other side. If you do that and solve for I out over IS, this gives you AI divided by 1 plus beta I times AI. The same concept. The gain after feedback is the same as the gain before the feedback divided by the amount of feedback. And the amount of feedback is 1 plus the loop gain, beta times A. Same thing if you'd like to find the input impedance and output impedance. Well, to find the input impedance, we're going to attach this source, Vx, measure the voltage and the current, and divide Vx over Ix is going to give us the resistance, input resistance with feedback. So Vx, if you look at this voltage, is the same as this voltage, right? So this Vx is the same as the voltage across Ri, which is the same as II times Ri, okay? However, II is the difference between Ix and If. So Ix is I in plus If. So you can substitute this with II times. And what's If? If is beta times IO. So substitute this one here. And IO at the same time, since this is shorted, is the same as AI times II. If you substitute all this in this equation here, you're going to get Ix equals this. Now we have an equation that links, you will have Ix here, and we have Vx here, just divide them, right? Divide Vx over Ix. So divide this by this, right? So II got cancelled, and you end up with Ri divided by 1 plus beta times AI. So the feedback impedance, input impedance, is the same as the input impedance without feedback, which is this one, divided by the amount of feedback, which is better, right? Because we need, for a current source, you need this to be smaller as possible, right? The current source, to deliver the current, you need to have, it needs to see a short circuit, right? So Ri now is reduced by dividing it by the amount of feedback. Same way we do it for the output impedance. We set that source to 0. Since this was a current source, we're going to open circuit it, and then connect the test source Vx and find the ratio of Vx over Ix. This is going to give us R out. Okay, let's start with Ix first. What's Ix? Ix is this current, okay, which is Vx. How much is this current? Now we cannot say this current is the same as this current, right? No, because now you don't have a short circuit. This current is divided here and here, right? So we need to find this current in terms of these two currents. So Ix is this current plus this current. This current is AI times II. This current is how much? Well, you can see that this node is shorted, right? So Vx is across RO. So if you divide Vx by RO, this gives you this current here. So this current is Vx over R. Now let's go to the II. We need to replace. We need to find an equation that links Ix and Vx only. Now this equation has Ix and Vx. This is constant, but this is not a constant. We need to get rid of this one. Now let's go to that input circuit. II is what? If you open circuit here, then II and IF are going to be the same, right? So if you look at this circuit here, this current is going to go this way, and this way, and comes here. So IF and II are the same, but they are opposite. There is a negative sign. So II and IF are negative, the same and negative. So IF in this circuit is fraction of IO, and IO in this case is IX, right? So this is going to be minus beta times IO, which is minus beta times Ix. Now we substitute this one for IA. So you remove IA and substitute it with this, you get this one here. Now you have an equation that has Ix and Vx only, and other parameters are constant. Then you rearrange the equation to get Ix in one side, Vx in one side, and then solve for Vx over Ix. This gives you this. So the same concept. Feedback, the output resistance with feedback is the output resistance without feedback multiplied by the amount of feedback. In this case, we need this to be very large or very small. Let's go back to the original circuit. We need this resistance to be very large or very small. Very large. We need this to be infinity so that all the current goes to the output. Okay? The load in this case is going to be connected at the output. Okay, this is a circuit here. Now, just before we do the analysis, I need you to recognize the feedback network, how to take it off, and how to find beta, okay? Okay, for this circuit, first of all, where is beta? Okay, beta. Maybe this was not in the previous slide, but take this note. Beta does not include RL or RS. Okay, so do not include RS or RL in beta. So don't say that beta is all these three resistors. No, it's just these two resistors. RL is not part of beta. RS also, if you have a series resistance of this for the source, or this one is not part. So can you tell me where is beta here? Is it these three resistors? No, it's just RF and R1. Okay, this is not part of beta. This is not part of beta. Okay. Beta is the network that connects the output to the input, right? Of course, this one is not included in beta because it's in the input only, right? This is not a feedback component. But here's confusing. Is this component part of the feedback or not? No, since this is the load, it's not part of the feedback. This is the resistance in which the current, the output current is going to pass to give you the power. So this is the output load. So it's not part of the feedback configuration. So you left with RF and R1. Because they are connecting the input and output, right? This one connects to the input, and this one also connects to the input. So these R1 and RF are part of the network, the feedback network. This is the same, okay? Now, this is a current amplifier, meaning this was a current and mixed as a current, which is in parallel or in shunt, and gives you an output current which is sampled in series, right? You need to sample this in series. Okay, this is why this circuit, this branch here is in series with the current, right? It's not in parallel. And you can see that this is not part of the output, okay? Because the output is here. Now let's take this beta off. So beta is like this, okay? this is RM, and this is RF. And this is V out, okay? And this is VF. Okay, but since we're talking about currents, we're gonna show this as current, okay? So I can put it this way, right? So this is I out, and where's IF? IF is going this way, so this is IF, okay? Now, can you have a current passing here without shorting this? So this has to be shorted so that you have a current flowing this way, okay? So, if you have this is the output of the beta, and this is the input. Number two, the port 2 is the input, and port 1 is the output, right? Output here, if you disconnect it, you have to short it to the ground for the current to flow. Otherwise, the IF is not going to flow, right? So you have to short circuit this one. Now, if you short circuit this one, can you give me a relationship between IO and IF? What's the relationship between IF and IO? Why is that? Because we know that beta is IF divided by IO. Okay? So what's the relationship between this current and this current? Okay, let's think of it this way. If you have a current entering this node, this current is going to split part of it here and part of it here, right? Let's call this I1 and this is I2. What's the I1? What's the value of I1? It's a current divider, right? So I1 is IO times this resistance, right? RM divided by RF plus R. You agree? And what's the relationship between I1 and IF?
Equal those.
Okay, so IF is negative I1. So in this case, IF is negative IO times RM over RF plus RM. Okay? So let's substitute this here. So this is going to be beta is going to be IO, the negative sign, RM divided by RF plus RM divided by IO. This is negative RM over RF plus R. So this is the value of it. Okay? Can you do the same way for this circuit? Let's remove the feedback network from the circuit. Okay? So it's going to be like this, right? This is R1, and this is RF, and this current here is IO, and this current here is IF. Now, if you disconnect, remember this one was connected here, right? It was connected to the input, right? IF. Now, if I cut here, what should I do with this side here for the current to flow? You should connect it to the ground, right? The same as we did here. We have to short circuit this one. Okay? In this case, you will have something like this. So this is R1, and this is RF, and this is the current IO, and this is the current IF, right? And this is the current I1. Right? You agree? So if you isolate the feedback network, which consists of R1 and RF, you're gonna cut here and cut here, right? And remove. Now, this has the current IO that comes from the amplifier. And this one, it has to be shorted for the current IF to flow. Since it's connected in shunt. And remember this, if it's shunt, shorted. Okay? It's like the same sound. Shunt, shorted. If it is series, leave it open. They call separate, or leave it open, leave it as it is. Okay, so can you give me the relationship now? What's the relationship between IO and IF in this circuit?
The IO is the sum of I1 and IF.
Okay, and let's do current KCL here, right? So IO is the same as this. Or you can do current divider, right? So this current is this current times this resistance divided by both. So IO is the same as IF is the same as IO times R1 divided by R1 plus RF. You agree with this or not? Okay. So we substitute this one here. So this becomes IO R1 over R1 plus RF divided by IO. Cancel this with this. So this is going to be R1 over R1 plus R. Okay. Why we need to find beta? For two reasons. The first reason is we know that what is the ideal value of the feedback gain? Ideally, remember the feedback gain is the feed forward divided by 1 plus A times beta, right? If this becomes very large compared to 1, what's going to happen to this one? No, if this is very large compared to 1, you're going to cancel the 1, and then cancel this, and this becomes 1 over. So beta is going to give you a rough estimate on the ideal feedback gain. By knowing beta, you know that the feedback gain, AI feedback, is roughly 1 over beta E, beta, which is going to be, in this case, R1 plus RF divided by R1, which is 1 plus RF over R1. So you know that your gain is roughly around this value after feedback. The second thing, if you know beta, and you know the loop gain, you can determine A. Because if you know beta, and you know that, for some, using analysis, you found A times beta. Since you know beta, so you know A times beta, and you know beta, then you can find, using these ones, you can find A. Right? You divide this by this, gives you A. So knowing the feedback gain, or actually factor, is very helpful, that it tells you how much is the ideal gain of your feedback amplifier, and also it gives you an estimate of the open loop gain of the amplifier. Okay, this one can follow the same analysis. Let's just do more training on finding beta, okay? For this one, where is beta? So this is a voltage source applied to amplifier, and then amplifier, operational amplifier, then operational amplifier is applied to a MOSFET transistor, and the load is here, and this is our feedback, okay? Now, where's the feedback network? It's only RF, right? Why? Because this one is not included. We cannot add RF in the, okay. Now, what is the relationship? So this takes voltage, right? This takes voltage. So the mixing is voltage, and the sensing is current. So this is a voltage to current, right? So this is a transconductance amplifier. Now, if we disconnect this one here, so let's disconnect it. We need to find beta here. So the question is, what's beta in this example? So I'm going to remove it from the circuit. So you will have something like this. Okay. This is our feedback. And you have a current here that's IO, right? And the feedback quantity is a voltage, right? VF. Do I need to short this to measure the voltage? No, if I short this, the voltage is going to be 0, right? So this is why I have to keep it open. Why? Because it's mixed in series, so I have to keep it open. Now we need to find beta. Beta in this case is a resistive network that has the relationship of VF divided by I out. Okay? Now, what's the relationship between VF and I out? RF, that's it. Because this current has no way to go this way because this is open. So this current is IO. IO times RF gives you beta. So the feedback beta is RF. So what's the optimum gain of this amplifier? What's A? In this case is going to be AG. Okay. Feedback is going to be 1 over beta Z, which is 1 over RF, roughly. Okay. So the ideal. In the practical case, you might find it, smaller than this a little bit. Okay. Let's do the same thing here. It's exactly the same, right? If you remove this, you have IO going this way, and VF is measured across RF. So VF is IO times RF, so beta is the same as this one. Okay? So in both cases, beta Z is RF. Let's do this case. This is measuring the voltage or sampling the voltage in shunt and mixing the current in shunt as well, right? This is shunt feedback, which is the transresistance amplifier. Now, can we find the beta? So beta in this case is going to be beta G, which is IF divided by V out. This current divided by this voltage. Okay? So let's now IF is going this way. V out is applied here, and this is RF. Now this is a current. Should I leave this open? No, I have to short it to measure the current, right? Or to sense it, to have the current passing. Now this current divided by this voltage is how much? IF with respect to V out. Well, V out is the current times the resistance, right? So it's RF, right? The relationship is RF, but there's a negative sign because this current makes this plus and this is minus, right? Which is opposite to this polarity. So there is a minus here.
Isn't it 1 over?
Yeah, isn't it 1 over RF?
Oh yeah, 1 over. That's true. Because this is the conductance, right? So let's do it this way. So V out is going to be minus IF R, right? Now if you find the ratio of IF over V out is minus 1 over R. So what's the final gain of this amplifier? The ideal gain of this amplifier. A Z feedback roughly is going to be ideal, is going to be minus R, which is the reciprocal of this one. But in reality, it's going to be less than that. You think this is the same or not? Same. IF goes this way, multiplied by RF gives you negative VR. Same thing. IF times RF gives you negative VR. So in both cases, beta G is going to be 1 over R. I know it's still confusing. How about this one? The same thing. IF times RF gives you VR. But with the examples, unfortunately, we don't have time today to solve the example, but next time I'm going to start with a new example. This table here summarizes all the 4 cases in terms of the gain, the input impedance, and the output impedance. You're going to find that the gain is reduced, always reduced by the amount of feedback. The input impedance is improved based on what you are mixing. Is it current or voltage? If it is voltage, then Rn has to increase. If it's current, then it has to reduce. And the output is the opposite. If it is voltage, RO has to reduce. If it's a current, RO has to reduce. Okay? And you always see that the series part has a larger impedance, and the shunt part has a smaller impedance. So this input is series, so it's larger. This output is shunt, the impedance is smaller. Shunt, series, this is smaller, this is larger. Series, both are larger. Shunt, both are smaller. Okay? Any questions? So, next Wednesday we're going to have our midterm exam. As I said, it's going to be, and also this Friday we're going to have the problem solving session over Zoom. You have the sign sheet. So, what time works best for everyone?
6 p.m.
6 p.m. 6 p.m. It's too late. Are you okay with 6 p.m.?
I think
Works.
closer to midday.
Hey, we're going to record it and post it on cameras, right? So, I'm fine, after any time after 2 p.m. I'm okay to do it in person or over Zoom, but I think over Zoom is going to be better to record it and have everything recorded. So how about like what time? 2, 3, 4, 5, 6?
I think
2 p.m.
We have a class from 11 to 11:50, right? 12, right? Okay, all right.
Let's do slightly after 2 because
I don't have that class.
I'll be back at 2 sharp.
Yeah.
So let's
Till to
make
4.
2:15 or 2:30. Okay, 2:30 on Friday.
By Zoom, right? By Zoom, right?
Zoom, yes.
Zoom, right?
Okay.
Yeah. 2:30 on Friday. So thank you.